right, guys, welcome to our next day looking at Hardy-Weinberg equilibrium. So today is Monday, March 23rd. And what we're going to do today is we're going to kind of do a really brief recap what Hardy-Weinberg equilibrium is. Sorry. And then how to determine if a population is in Hardy-Weinberg equilibrium. So you are going to want to take out some pencil and paper to take notes, because what I'm going to have you guys do is take notes again during this whole PowerPoint presentation. So I'm going to run through some background notes about Hardy-Weinberg equilibrium that we didn't quite go over yesterday. So you're going to want to record that information, and then also whatever work we do on the whiteboard then is also going to be written down. You're going to take a picture of these notes and then just send it to me using that Remind app, and then that will count as your participation and credit and attendance for today. Because there is no exit slip in the end, this is going to be kind of like your exit slip. All right, let's go ahead and get started. Go ahead and hide this little guy here. And so again, if you need to, pause, I'm going too fast, make sure you do so. So as a quick recap, again, we're in the evolution unit, and evolution, is a very basic definition, is looking at changes in allele frequencies within a population over time. So these alleles are coding for different traits that we have. And so if there are, certain traits becoming more or less common in a population, we know that the frequency of those alleles for that trait are becoming more or less common in that population. Therefore, changes are occurring and evolution is occurring. And so if a population is in Hardy-Weinberg equilibrium, that means that evolution is not occurring and that these frequency of alleles will not change. That's what we're going to show you how to calculate today. We are looking at diploid organisms in this situation. So that's what we're kind of focusing on in that evolutionary aspect. And just as a reminder, diploid organisms, to be diploid, that means you have 2 copies of every single type of chromosome. And on those chromosomes, you have all those different genes. Because you have, 2 copies of every chromosome, therefore you have 2 copies of every gene as well. So again, there are going to be some traits within humans that are coded for more by more than one allele, but we're kind of excluding those traits in this situation. So to figure out what's the total number of alleles for a given gene in a population. So you want to find what's the total number, the gene pool for this particular gene. What you do is you take 2, because again, individuals have 2 copies of every single trait for every single gene, 2 alleles for that, and then you're going to multiply that by n. And in this situation, n is going to be number of individuals in a population. So let's say you have 500 individuals in a population, and for a given trait, you want to figure out, okay, what's my total number of alleles for this given trait? Let's say flower color. We take 2 times that 500, and they're going to be 1,000 alleles in that population coding for flower color. And we're looking at Mendelian traits in Hardy-Weinberg equilibrium. So looking at traits that are coded for by 2 alleles, and you're going to have the dominant form of that allele and then the recessive form in that allele. And there is an equation we're going to be using to calculate Hardy-Weinberg equilibrium. And there are different variables or letters that they are using to represent these different alleles. So in the Hardy-Weinberg equilibrium, we're going to use the letter P. P is going to represent the frequency of the dominant allele, let's say capital A. And then Q is going to represent the frequency of the recessive allele, let's say little a. So if you add up those 2 frequencies together, the frequency of the dominant allele plus the frequency of the recessive allele, that should equal to 1.0. If it's not, then you maybe want to go back and check your math. And so we know the frequencies of those 2 alleles, the dominant and recessive form. We can then figure out the frequency of different types of genotypes in that population. So you can actually interpret these frequency values as percents. And so those 2% must add up to a total of 100. So what percent of the population has the dominant allele? What percent of the population has the recessive allele? And then with that, there are three different combinations of genotypes. You can either be homozygous dominant. So if you know the frequency of the dominant allele alone, you can then figure out what percent of the population is homozygous dominant for that particular trait. If you know the frequency of those two alleles, you can then figure out, what percent of my population is heterozygous for that trait. And then you can also figure out what percent of my population is homozygous recessive. So you're going to be wanting to know this information as like your starting point. So then you know what those frequencies are initially in your population. And so if you go back later, 1, 2, 3, 50 generations later, you can see if those frequencies or percents have changed. If these frequencies have not changed, then therefore your population is not evolving. But if these percents have changed, therefore your population is evolving. And so there's an equation we're going to be using to kind of put all these three frequencies of these different genotypes together. And this is the equation here. So it's p squared plus 2pq plus q squared equals what? So let me walk you through what this means. So p, again, is looking at the frequency of your dominant allele. So p squared is going to be representing the frequency of my individuals that are homozygous dominant. Because in order to be homozygous dominant, you must have 2 copies of that dominant allele. So again, 2 copies, of p, so p squared. So that'd be the frequency of individuals that are homozygous dominant in a population. And then to figure out the frequency of heterozygous individuals, remember if you're heterozygous, you have one of each allele. You have one dominant, one recessive allele, even, but you're expressing that dominant trait. So you have a P and a Q. However, there are 2 different ways that you could be heterozygous, meaning your mom either could have given you the dominant allele and then your dad the recessive, or your dad could have given you the dominant allele and your mother the recessive. So there's 2 different ways to be heterozygous. So we add plus 2pq. And then we add in the individuals that are homozygous recessive. And to be homozygous recessive, you must have 2 copies of that recessive allele, so q squared. So the reason why it equals to 1 does not mean that it's in Hardy-Weinberg equilibrium. It's just a way for you to check your math to make sure you got the frequencies calculated correctly. Because all of these 3 frequencies must add up to 1. So just imagine if these are 3 different percents, all 3 percents must add up to 100. You're looking at the whole population. Oh, sorry, that was just pointing out that there's 2 different ways to be heterozygotes. So just to reiterate, if we are calculating these frequencies of the alleles and their genotypes over multiple generations, even after just 1 generation, or even after 50 generations, and they're not changing, therefore the population is not evolving, and it is in Hardy-Weinberg equilibrium. However, if you go out even 1 generation later, even 50, and you notice that those frequencies are not the same, that they are starting to change, even if it's a slow change, that means, population is evolving. So those frequencies that are changing is indicating, that they are potentially evolving. And if that's the case, therefore the population is not in Hardy-Weinberg equilibrium. All right, so in order to do this, it's probably a lot easier to see if I switch to my whiteboard. So I'm going to end this little video feed here in a second, and then we'll work through how do we figure this out. So you are going to want a lot of room on your paper because it's like calculus in a way where it's just multiple steps in order to get to the end result. So please bear with me during that time. But anyways, let's say we're looking at a population of iguanas and a particular trait and seeing if that trait is becoming more or less common in the population. Because if it is, that means that population is evolving. And so let's say we're looking at webbed versus non-webbed feet in iguanas. And so let's say non-webbing having no extra membrane in between their toes is dominant. So we'll represent that with a capital W, versus having webbed feet where you do have that extra membrane between your toes. Let's say that's recessive, and we'll represent that with a little W. And so this is your question you want to answer, and it is going to help you answer the overall question in the end: is my population in Hardy-Weinberg equilibrium or not? So let's say you wanted to see, is this trait of having non-webbing feet becoming more common in this population? So you want to know, are those allele frequencies changing? Because in the end, that will tell us if it's in Hardy-Weinberg equilibrium or not. Anyways, so in order to do this, we need to know two things. One, what is the starting population? What do those frequencies look like? And then we're going to imagine ourselves going back out a few generations later, taking the exact same information, looking at those frequencies, have they changed? All right, see you on the whiteboard.